This lecture is going to look at chapter 9 from the book, which is looking at integer programming algorithms. So first off, what do we mean by integer programs? Well, by integer program, we mean something where the variables have to be integers. We already kind of saw this when we went back to the Hungarian method, where our variables had to be 0 or 1. So that's actually a binary problem, but it's an integer problem. The numbers have to be integers. You can't be a half or a quarter or so forth. So as an example, this problem that we're given here, we're flying cargo and the cargo is in bundles. We can't split open those bundles. They have to go as units. So because they have to go as units, you can't send a half a unit. You have to send a full unit. So you have to divide it amongst the different different ways of transport. So this is an example of an integer program. So you can write this out as a linear program, and you put the extra condition that xi is integer or is integral. That turns into an integer program. So for example, here is an integer program written out where we say that the variables are integral. Now you're going to run across a couple of different types. One is a pure integer program, such as this one, where everything has to be an integer. Now note that if all of your main variables are integers and all of your constraints and so forth are all integer numbers, that also means your slack variables are also integers. There is another kind called a mixed integer program where only some things have to be integers. Okay? That is even more complex to solve depending on the method that you're using, but it is another common type of problem. When we talk about integer programming, we will often talk about something called the LP relaxation. So in other words, this means you have your problem, your integer program, where things have to be integers. Forget about the integers and just solve it as if it were a normal program. That's called the LP relaxation. Now, one thing to note about the LP relaxation, your optimum value for the LP relaxation is always equal to or better than the integer problem. For example, you take the one that's here and you solve this without the integer restriction. Then you solve it with the integer restriction. Your solution with no integer restriction will always be equal to or better than the solution with the integer restriction. Which makes sense because the integer restriction is just adding a new constraint or a new restriction on your problem. The more restrictions you add, the more constrained you are, and the worse your solution can potentially be. You can never get better by putting more restrictions on your solution. Okay? Sometimes it'll be the same, but it will never be any better than your relaxation problem. Now, first thing is, why can't we just round? Well, if we solve a linear program and round, we will usually get a very good solution. But the problem is you don't always get the best solution. So take this one, for instance, this problem. You solve the LP relaxation. So in other words, forget about them being integers and just solve it as a simple linear program. What are you going to get? That's your solution. So if you round that, you are going to get x equals 2, y equals 3, and u equals whatever that it works out to. Problem is that that isn't the best solution. When you actually round it, or when you actually solve it with the integer restriction, you get x equals 5, y equals 3, and u equals 32. Okay, so note that this was a minimization problem. Our LP relaxation had a minimum of 24. With the integers, we have a minimum of 32. It's never as good, or it's never any better. So our minimum isn't as small, but our actual solution looks nothing like the rounded solution from the LP relaxation. So rounding does not guarantee that you are going to get the optimum solution. I should also note that if you're using Excel, Excel has an option for your variables to be integers. So you can also use the Excel solver to solve integer programming. And I'm going to say right up front, solving integer programming is much more computationally expensive than solving a simple linear program. It's much more difficult to do, it takes more time, and especially for large problems, it can become very expensive and very time consuming to solve integer programs. Here's another rounding one. So you can see a linear program here. The one we just saw a minute ago, well, we rounded it wasn't quite the solution, but the solution wasn't very far away from it. Here, if you solve this one with the LP relaxation, there's a solution you get. You round it, you're going to get x equals 0, y equals 2. The actual optimal solution is x equals 7 and y equals 0. So in the previous one, even though we rounded it and we saw it wasn't the solution wasn't too far away from what we rounded it to. In this one, you can see the solution is very different from your rounded values. So rounding is usually not a good strategy unless you have some idea of what's going to happen when you round it. So we're going to see a couple of methods here. We're going to see two things. One is called a cut method and one is called a branch and bound. And these are two ways of solving integer programs. So first we're going to deal with the cutting method. The cutting method, you start with your linear program and you solve the LP relaxation. Most integer programs solutions say solve the LP relaxation and then change your original problem around. Okay, so that's what we're going to do here. We take our problem and we solve it. Then what we're going to do is we're going to take a look and see, okay, what variables come up non-integers. If everything comes up as an integer, we're done. If some of our variables, the solutions, are non-integers, we are going to add a new constraint to it that is going to restrict our solution and is going to kind of hide, it's going to take that non-integer solution that we found and put it outside the feasible region so it is no longer a viable solution. That's the basic strategy of doing a cut. So for the above equation, when you solve the LP relaxation, you get a solution of x1 equals 9 over 5 and x2 equals 0. You're going to add a new constraint in, x1 plus 2x2 is less than or equal to 1. Now, how do you find that constraint? That's what we're going to go into. There's actually a number of methods of finding that new constraint to add in, but we're going to see something called either it's called the fractional cut in the book. Many other books call it the Gomery cut method. So that's what we're going to look at. How do you determine what that new constraint is? The way we're going to see isn't the only way of getting this constraint, but it is one way of getting it. Once you add in that constraint, you again solve the LP relaxation of the resulting problem with the new constraint, and you come out with a new solution. Then you do the same thing. If there's a non-integral solution, you solve it again. Add a new cut and solve it again. So the problem with this is, how do you find the cut? In other words, how do you find that new constraint? And the second thing is, how many are needed? Some of them work very efficiently with this method. Some linear problems actually take a long time with this method. So first we're going to define something. We're going to define a function. We're going to say that this bracketed x to be the largest whole number less than or equal to x. So for instance, if we have negative 2.25, it's going to be negative 3. So we're looking for the whole number rounding down, which in this case would be negative 3. And we're going to define f of x to be the fractional part, the positive fractional part of that number. So in this example that we have here, f of negative 2.25 is actually equal to 0.75. So it's the distance the number is away from the integer below it. Okay, so we're going to use that function to build our cut. So here is the Gomery cut method. This is an overview, then we're going to go into some examples. So first off, make sure your constraints all have integral coefficients. Every number there has to be an integer. So in other words, if your constraint has 1/2 x1, just double your entire constraint. Multiply it through by 2. Make sure that every number you start with is an integer to start with. Otherwise, this isn't going to work. Solve the LP relaxation. If you have all integers, you're done. Okay. In that case, your optimum constraint, your optimum values actually is all integers. You don't have to do anything. If you do have a fraction or a non-integer as one of your variable solutions, pick one of them. You could have multiple ones. Just pick one, and we're going to build a new constraint out of that. So when you have that, you can take that constraint and write it this way. You can write it as your original constraint minus your coefficient is equal to the negative of your slack variable. Okay. Now you are going to add this constraint. Remember that function we saw before where you pull out the fractional part? It's the fractional part of all your coefficients minus the fractional part of your b, your right-hand side coefficient, is greater than or equal to 0. That is equivalent to this, where this is now a new slack variable. So what you're doing is you are going to introduce a new constraint and a new slack variable. Resolve the linear program. This should be resolve the LP relaxation of the new linear program and return to step 2. Okay. So where does this new constraint come from and how do we calculate it? This is called the fractional cut or the Gomery cut. And here's what we're doing. So here is our linear program and we put it into a tableau. Do one pivot on your tableau, you come out with this. Note now that you have your solution, you have optimized it, but your two variables have fractional solutions. So we're going to have to take one of these and do something to it to add the cut in. And you can pick either one. In this case, we're going to pick this first one. So this is the linear program rewritten based on that final tableau. So we take our constraint, that's pulling out that first constraint, and you can see that the x3 is the slack variable in there. Rewrite each of these things, breaking it up into the fractional and integer portion. So 122 over 5 is 22 and 2/5, so write it out as 24 and 2/5. Plus -1 plus 1/5 plus x3 equals 9 plus 4/5. You're taking every number that's in there, every fraction, and breaking it up into an integral portion and a positive non-integral portion. Now that you have it written out like that, take all the integers to the left side, all the integers to the right side, and you end up with this. So you can see this is the exact same thing that we started with. I've just rewritten it with all the integer parts on the left and all the fractions on the right. So you can see where we're going with calling it the fractional method, because we've gathered all the fractional parts of our constraint. Okay, so now take a look at this right-hand side. What does it tell you? Well, remember, all of our variables are positive and they're integers. Because they're positive and because of the way we built this, remember we said we had to take that positive fractional part? That's that f of x. So that positive fractional part when we swing it over to the right-hand side, becomes negative. So we have a negative number times a variable minus a number times a variable. All of the coefficients in front of the variables on the right-hand side are negative, except for the constant. So because all of our variables have to be positive, so remember our problem says everything has to be positive, that means we have a negative number, another negative number, and so on, and just a single positive number. So that means that the x2 and x4 can be 0, or they can be something larger, but no matter what they are, because they're positive, that equation, which is the right-hand side, has to be less than or equal to the value of our constant. So that's just pulling out the right-hand side and noting that this can never be any larger than 4 over 5 because my variables are all positive. But now I can make another note. Our 4 over 5 is the fractional portion, but all of my variables have to be integers. In particular, if you look at the left side of the equation, everything there is an integer. So that means that the right-hand side has to be an integer as well. So our negative 2 over 5 x2 minus 1 over 5 x4 plus 4 over 5 has to be an integer, and it has to be less than 4 over 5. So it can't be anything between 0 and 4 over 5. That means it has to be less than or equal to 0 because it's also an integer. It's equal to an equation that has only integers, so it itself has to be an integer value, which means it can't be 4 over 5. It can be no more than 0. In fact, because of the way we built this is always going to be a number between 0 and 1. So that means that what I have on the right-hand side is going to be less than or equal to 0. So now what do I have? I have a new constraint. I have found I have rewritten everything to say some of these variables have to be less than or equal to 4 over 5. That's not adding anything new. But then I note that this has to be an integer. So I can ignore the 4 over 5 and change it to a 0 because it has to be an integer. So now I just rewrite it with a new slack variable, taking my constant over to the right-hand side, and here is my new constraint. So this is giving me more information. It isn't eliminating, the only thing it's going to eliminate is the integral, or the fractional value, the decimal values. Because everything is an integer, I have been very smart in picking this, and it is adding some new information, making use of the fact that it's an integer, and giving me a new constraint that I can now add into my problem. So this was my optimal solution for my LP relaxation, which gave me this tableau. I add in that new constraint. Here is the new constraint that I just calculated. And as I said, what it does is it only eliminates a single solution and forces things to be an integer around that solution. In my tableau, this now adds in a new row representing the new constraint, and a new column representing the new slack variable. So I have expanded my tableau, but now I can take this and I can solve it. With another LP relaxation, I can solve it and I get a new solution. And I just keep doing this over and over again. But note that this tableau now, if you look on the right-hand side of this tableau, I have a negative number. What does that mean? That means I use my dual simplex method. So that dual is rearing its head again here. Use the dual simplex method now to solve the tableau or the linear program with the new constraint. And then see if that solution now has non-integer values, you do the same thing again. You put on another cut. That's one solution, one way of solving it with the cuts. There is a second way of doing these, which is called branch and bound. And again, this involves solving your linear program, your LP relaxation of your integer program, and it is also a way that you can handle mixed integer programs. I should mention that for the Gomery cut, if you're doing mixed integer programs with the Gomery cut, there is a way of doing it, but it is very complex. So we're not going to go into that right now. The branch and bound method gives you, this method also works very well for both pure integer and mixed integer problems. And what we do for the branch and bound method, what we're going to do is solve our LP relaxation. We're going to pick a non-integer solution or a non-integer variable. Then we're going to say that we're going to force this one to be an integer and solve it again. So, for instance, here is a linear program, an integer linear program. When you solve this, the LP relaxation, you end up x equals 0 and y equals 3.5. Now with the Gomery cut, you would add a new constraint. With the branch and bound, what you do is you duplicate your linear program, each of which have a new constraint. So you end up solving twice as many. So you're going to create two LPs. See, the problem here is that y is 3.5, and it has to be an integer. Well, what does that mean? That means that y either has to be 3 or less, or 4 or more. So what we're going to do is eliminate everything between 3 and 4 with our new programs. So we're going to create a second linear program, which is the exact same, just with the additional constraint, y is less than or equal to 3. And we're going to create a second one, where y is greater than or equal to 4, and we're going to solve both of these. And we're going to see if we come up with integer solutions. So what we've done is we have noticed our linear program relaxation has a non-integer solution, and we've created two new problems that eliminate that solution. So it forces you to find a new solution, and then you see if it's an integer or not. So you can kind of see the solution to this. You can diagram it out. So the top node on here represents our initial linear program. That's our initial linear relaxation. We end up with x equals 0, y equals 3.5. Well, now we want to eliminate everything where y is between 3 and 4. So either y is less than or equal to 3, or y is greater than or equal to 4. When you add in that constraint, y less than or equal to 3, resolve your linear program, you get that as a solution. So again, note that we have a fraction in there. On the other one, where you put y is greater than or equal to 4, you try to solve it out, it's going to be infeasible. So you can't go there. So now we have a new linear LP relaxation, a single problem now. We have a new fraction. So what we're going to do is we're going to split that up again. We're now going to take that second linear program. We're going to add in that x has to be less than or equal to 0. Solve that. We're also going to do it again where x is greater than or equal to 1 and solve that. So now we get more solutions. When we add in the constraint x less than or equal to 0, we get this on the left-hand side. When we add in the constraint x greater than or equal to 1, we get that solution on the right-hand side. Now we're being asked to maximize. Notice that both of these have integer solutions. So these are as good as it's going to get. We're asked to maximize our function. So we just pick the one with the largest number. And there's our solution. So our solution is x equals 0, y equals 3, and u equals 12. And that's the branch and bound method. It's continually solving new linear programs where you're adding in a new constraint. And at each branch, it divides into two new linear programs. So as you can imagine, this can grow quite a bit if you have a lot of variables that end up being fractions. This can also be inefficient. So for instance, this is an innocent looking linear program, looks pretty simple. If you try to use the branch and bound operation on this, you're going to go through 11 nodes, a simple two variable problem. You're going to go through 11 nodes before the solution is found. With the Gomery cut, one single cut will give you the answer. So in this case, the Gomery cut is way more efficient than the branch and bound. But in other cases, the branch and bound is going to be more efficient than the Gomery cut. And the catch is, there's not really a good way of telling which one is going to be the more efficient solution when you embark on solving one of these problems. They just give you two different problems, two different methods to solve your problem. So we talked at the start about the rounded solution being often not optimal. And we saw some cases where the rounded solution was a long ways away. In reality, though, solving integer programs, especially for large problems, is very expensive. It is computationally, it takes a lot. Sometimes that rounding is going to be good enough that you're going to be okay with it. And how can you tell that? Or how can you get an idea of it? Well, even though when we see a problem, when we solve the linear relaxation, and remember, solving a linear LP relaxation is very efficient. We can solve that and we know that this is an upper bound on our maximum, assuming we've got a maximum problem. So we can solve our LP relaxation pretty easily, and we call that U star. Okay, that is the optimum solution for our LP relaxation. We can then round to get something new. We call that UR. So just take your solution and you round it, round all the variables, and calculate U. That gives you what's called UR. So it's the rounded solution. Now the catch is that our actual optimal solution for the integer solution, for the integer problem, is somewhere between those two. So if you solve your linear relaxation, you get some fractional numbers. Quite often in reality, especially with large problems, what you'll do first is you'll round. You'll try the rounded solution. Sometimes that rounded solution, the optimum value is going to be very close to what you originally, to your solution for the LP relaxation. So if your U star and your UR are very close, what you know is that your optimal solution for the integer problem is somewhere in between. And sometimes that's good enough. Sometimes you don't need the exact opposite, but if you have a solution that is within 99% of your optimum, you're happy with that. And you can go with that because it will take a long time to compute the actual optimal solution. So in the real world, even though the rounding does not usually give you the solution, sometimes it's close enough. And finding these two values will give you an idea of just how close it can be. So depending on your situation, sometimes rounding is okay. But that's a real world implication of it. Okay, so that is integer programming. That are two methods for integer programming.